Hello again, this is the third video in our series about the European sword. This video series follows a logic sequence and when not followed will cause misunderstandings. So I would encourage you to start always with my first video and then follow the numerical sequence. But let's get to the third video now. Welcome to this channel. The heat treatment was the main topic of the last video, and we found out that carbon plays an important role in it. But what steel is exactly used for European swords? Well, there are not even so many different steel types in play. I will use the designation of steel used by the American Iron and Steel Institute, AISI. AISI uses mostly only 4 digits to describe the steel we are looking at.
The first 2 digits are used to specify the alloying element in the steel. The second 2 digits indicate the so important carbon amount. You should know why this is so important by now. We could also say the first 2 numbers indicate the type of material that was added to the iron, and the second 2 numbers indicate the amount of carbon in the steel. It gets normally a little more diverse, but we will do fine with the 4-digit system most of the time. The first 3 common sword steels are 1045, 1060 and 1095. 10 stands for plain carbon steel, so no significant influence by another alloy material is present. However, the manganese content can go up to 1% max. 45 means actually 0.45% carbon content. So 1045 is, if you want, normal steel with 0.45% carbon. 1060 is normal steel with 0.60% carbon. 1095 is normal steel with 0.95% carbon. This brings me to the first issue. Now this is important. A steel with more than 0.22% carbon content has very bad welding properties. You should not even think of trying to weld a European sword blade because it has for sure at least 0.45% carbon and can have easily 1% carbon if it is made out of 1095 steel. So a welded rod on a blade is absolutely a no-go. Don't even try to find a reason to do it except you don't want to use this blade and hang it at the wall. In this case I would rather go with a wooden sword because it will be stronger than the welded one. Through the heat of the welding process and the high carbon content in the blade we get a brittle layer between the weld and the attached material. Since welding is done through excessive local heating, the heat is drawn very fast into the surrounding cold metal. You distort the whole lattice of the steel grid. And worse, you create a brittle layer where you want to attach the pieces. Don't do it, and don't try it, and don't justify it. Blade steel should never under any circumstances be welded, period. Now let's continue with the material that your blade is made of, hopefully in one piece as blade and tang. The minimum carbon content for quench hardening is 0.35%. Now you know why we start with 1045 steel, and now you know that hardened blades must not be welded. In our example we have 1045, 1060 and 1095 steel. Which one is best, you may ask? Like always, the answer is not so easy. Principally, the hardenability and reachable hardness level of 1045 steel is sufficient enough for a good blade.
But there are differences, of course. Generally talking, the more carbon, the harder the blade. The harder the blade, the harder the smith has to work on it, and the more expensive the blade gets. The harder, the less forgiving in heat treatment is also a factor. See, the carbon content changes also the right temperatures of the appropriate heat treatment. I rather have a more forgiving blade than a very petite one, and at the end it depends more where you buy your blade from. If you are wealthy and you can afford paying a smith making you a sword, then my approach would be whatever material he is experienced with and used to should be the steel of your blade. It is not good to force a smith in having to work on a material he is not or little accustomed with. So at the end it depends more on the quality, heat treatment and professionality of the smith than on the material, as long as the material is good for blades. I am not rich and therefore I order from the internet, so the above is not my case. If I want to buy a blade, I look for a known company with experience, knowing that those companies can have good and bad swords in their selection. We go only for the good ones, of course. Unfortunately, we cannot try the sword, but they should provide us with some data at least. The following data should be or has to be mentioned. Weight in total. Hardness of the blade. If possible, quenching type. If possible, hardness of the tang. Length of the blade. Point of balance. The material it was made of. Thickness of the blade. Width of the blade. Grip length. And how the pommel is mounted. And maybe even the pivot point. There's also the information on other websites, of course, that give you maybe even a test review of the specific sword you desire. See, it is more important how the producer is able to work with the material, as long as the material is good for swords, than to focus only on the specific kind of material that is used. And that makes all the difference.
There's also 5160 and 9260 steel. This is spring steel, especially 5160 is used as leaf springs in the automotive sector. I can hardly think of a more demanding job than to be used as a leaf spring on a truck. This is a very good blade steel, and if heat treated right, will be one of the best. 51 stands for the certain chromium content that is about 0.7% to 0.9%. Our manganese can also be up to 1%. Silicium is present, but as little as 0.15% to 0.3%. So it is basically a 1060 steel with a influential chromium content. The effect of chromium in steel depends on the amount of it. Chrome in this amount increases the toughness, ductility and tensile strength. This is good, but if the chromium content is 11% and higher, to get a stainless steel would be very bad. The blade that is made out of that material should better be for the kitchen knife. Stainless steel is not usable for sword blades except wall hangers. The too high chromium content makes the blade very brittle and therefore prone for breaking. 9260 is a more seldomly used steel and is supposedly, because of the amount of silicon in the steel, high flexible, meaning you can bend it very strongly and it will find its shape again without breaking. Those tests are always done with the flat side of the blade, of course. The behavior with the edge hitting a target is not reflected in those tests, but chances are that you won't come across this type of steel in the European swords.
There are also more exotic steels like T10 or L6 and S7 steel. I don't plan to go into those because of their exclusivity. To tell you the truth, I feel uncomfortably to talk about this material issue because I have not enough experience to come to specific conclusions, and neither do I have the possibilities to change that. What I can say is 1045, 1060, 1095 and 5160 are the usual typical steels for blades, and all of them will do if treated right. What you may also come across is the Damascus steel. We use normally mono steel for blades. So what is Damascus steel?
For a smith to make a blade out of not homogeneous raw steel pieces means to draw out impurities and to distribute the differences as evenly as he can throughout the whole block of steel. This is especially true if carbon is not distributed evenly in the block. The smith folds the steel often to reach this effect. The more even the steel block is in its consistency, the better the blade will be. But what happens if the smith can get already high quality steel from the steel industry? Yes, the steel from the industry is much better than traditionally produced steel. It may not be as romantic to get the steel from the industry, but you get for sure a better steel for the blade. It is simply cheaper and better. And best of all, people like you and me can afford to buy swords.
So why are there Damascus blades still out there? Well, it is a more cosmetic approach than to have a better blade. Technically, it makes no sense to have a Damascus steel blade. To the contrary, Damascus steel blades will be more likely not as good as modern mono steel blades. A lot of problems can come with Damascus steel. The layers don't bound as good as the mono steel with the no layers does. If there are different steel kinds layered together, you most likely don't get a positive effect out of the different properties of the used steel, but internal weaknesses can be present. Imagine quench hardening is already difficult enough, but the internal different behavior of the different carbon content layers can cause a lot of extra tension and problems in the blade. Today, mono steel is the best. If you want to appreciate your mono steel blade really, then watch an internet video about industrial steel production. There you can see that only the large amount of steel output allows us to have steel at an affordable price. There is so much energy and work in the steel already present before the smith creates a blade out of it. For romantic and ritual or ceremonial or artistic purposes, a Damascus steel blade may be more attractive. I know that Damascus steel was a special steel folded in the past, and we don't know anymore what exact technique was used and how it was done. With these explanations, I am referring to the nowadays offered blades that are running under the name Damascus steel blades. Should your sword be made out of steel with a lot of impurities in it, in an uneven distribution carbon content, this system of folding steel gives the best results that the smith can do. The industry liquefies the whole metal into a soup and bounds and burns the impurities out. How would you rather mix components together? By mixing them in a liquid state or by mixing them in a solid state? This is why industrial steel is purer and better. At the end of this topic, we can say mono steel is better than Damascus steel. Sword blades must not be welded. stainless steel is not suitable for saw blades, and even the best blade material can be messed up by wrong applied techniques and foremost wrong applied heat treatment. Now the last topic for video 3 is the blade's cross-section. The cross-section of a blade is important for the use of the sword. If you want to have a stiff, thrusting, optimized sword, you should look for a diamond form along the whole blade with a central ridge. If you want to have a compromise between thrusting, cutting and slashing, a mix of fuller on the bottom of the blade and a shallow diamond on the top of the blade can work very well. There are much more cross-section variants out there, and every one of them has a unique ability.
When we talk about the cross-section of a blade, then we talk about the three wonders of the sword: thrust, cut, blow. The normal diamond is a pretty simple and straightforward design. It is especially good in giving the blade stiffness perpendicular to the edge line. Therefore, the vibration is reduced and the thrusting ability is increased. However, the blade width from edge to edge is limited, and this can lead to a less strong blade if it comes to direct edge-to-edge impact, which is partially compensated by the higher amount of blade material that can be put to work. The thicker cross-section is not the optimum for cutting though. The edge of this type of cross-section is very easy to be reached, but a less optimal angle has to be used to resharpen the edge, otherwise the whole area of the big edge flanks all the way to the middle of the blade would have to be grinded. The hollow ground cross-section is a compromise of the normal diamond and increases the cutting ability. The edge has a very small angle and is therefore very sharp. This increases the cutting abilities even more. The blade loses overall weight on the positive side, but loses also strength on the downside. Stiffness is not a lot compromised, and we have still a good thruster. Resharpening is easy by using a bigger edge angle, and that is not a problem, because the edge angle will be still very little even if made a little bigger. However, the concave shape can hinder sharpening tools to reach the edge easily. Hexagonal cross-sections are less stiff than diamond ones, but allow wide blades. This is advantageous for edge-to-edge collision, for example. The edge by itself is not as sharp as the hollow ground and is approximately the same as the normal diamond. However, cutting resistance is reduced because of the thinner blade cross-section. The blade is not so good in thrusting because of the less stiffness. Resharpening is easy and allows the same edge angles by grinding the little flanks. The thickened diamond is not used in our kind of swords and is basically a square cross-section that gives maximum thrusting abilities for toothpick-like blades. Cutting and hitting abilities are dismissed by this extreme one-sided approach. Lenticular is basically a rounded hexagonal cross-section and shows basically the same features as a hexagonal shape. A lenticular blade would be a little bit heavier and stiffer than a hexagonal one, so slightly better stiffness and therefore increased thrusting and impact ability. Cutting is slightly worse because of the little increased edge angle and the blade thickness. Resharpen is easy because of the convex shape of the blade, so tools can be applied easily. This lenticular blade comes normally with a fuller or even a double fuller or broad fuller. The purpose of the fuller was already mentioned, and like I said, it is a very smart way to reduce the weight of a blade or to make a blade broader with the same amount of blade material. Usually the blade loses stiffness that is needed by thrusting, but gets a better cutting and hitting impact performance that comes with the thinner and broader blade. Very broad blades demand a not gradual profile taper. The profile taper has to narrow, so to say, in stages towards the point. The blade gets a convex look and can be very pointy while keeping a long enough cross-section at the wick with this geometry. A long enough cross-section at the wick is desirable because this is the most used impact area on the sword hitting a target.
This concludes the video 3 of the sword series, but one more point about the straight blade shape. If you ever go into HEMA style longsword fighting, you will get a revelation about sword handling and the possibilities thereof. A two-edged sword has to be straight if both sides of the blade should be used equally and permanently. There are curved sword blades with one long edge, the true edge, and a mostly crippled wrong edge from the point a little inward. Yes, you can use this wrong edge also in fighting, but to use a blade permanently with both sides being able to make fast direction changes and still threatening the opponent with a maximum of lethality is only possible with straight two-edged blades like the typical medieval European sword. Straight blades like to be turned in their longitudinal axis, while curved ones resist, which means also that curved blades stabilize themselves during chopping. Ironically, straight blades don't have to be turned all the time because of their two opposite edges. But their alignment by chopping comes mostly with training. No real help comes from the blade. Straight blades like to thrust with their center point. The whole geometry and weight is behind the point and supports the impact. The different strikes with their subsequent follow-on moves are fantastic rich with a straight two-edged sword. Having said this, we have to understand that even in the Crusades, the European armies, especially the Franks, had a strong armored infantry force that could withstand cavalry and used efficiently was superior on the battlefield. The European approach is also to train on a weapon intensively. This is for me the point. As a straight blade offers a lot of possibilities, it demands also a lot of training. If you have a lot of people and a lot of horses, let's say, you might focus more on the easiness to handle a weapon. This approach is valid and successful and reflected in modern armies as well. Sometimes it is not advisable to put too much energy into a system that can be even inferior if not enough skill is achieved. An army based on cavalry and big in number should go probably for the curved blade as it shows more intuitive behavior and at the end is easier to handle. This allows also to share the attention with other things than only to focus on the sword. The sword, especially the longsword, doesn't like to share with anything. It grants you a lot of power if you focus on it solely, but it is not a good side weapon and therefore the circumstances and abilities dictate the kind of weapons used at the moment. For example, let's say I can make 3 not so work intensive swords with the same energy demand of making 1 longsword. And I have a lot of people available for my army. I would rather arm 3 men with not so work intensive swords than 1 man with a superior one. Now the other way around. If I have not so many people available, I rather train them well and give them the best swords. This is only one facet of the whole issue with curved blades and straight blades. But if I just look at the possible potential of a sword, I would favor the straight double-edged blade over the curved one, knowing that there are circumstantial factors that hinder the straight sword to come out more favorably. This leaves a lot open and there is so much more to say about it, but I have to leave it to another time, so bye and I'll be back.